Dear students, under the topic vector differentiation, here we have a significant problem that has appeared in one of the end semester examination. The question is, prove that a vector given by 2x plus yz I vector plus 4y plus xz j vector minus 6z minus xy k vector is solenoidal and as well as irrotational. Also, find the scalar potential of the given A vector. Now, here we have three questions, that is, A vector is given to us and we are asked to prove that it is solenoidal and as well as irrotational. And the third question is we have to find the scalar potential of the given A vector. So, first of all, in order to prove that solenoidal, we have to prove that nebula dot A vector is equal to 0. So this will imply that A vector is solenoidal. Secondly, we have to prove that it is irrotational, for which we have to prove that nebula cross A vector is equals 0. So that will imply A vector is irrotational. And thirdly, we have to find the scalar potential of A. If phi is the scalar potential, then there will exist a function f vectors such that it will be equal to nebula phi. So that is the gradient of phi. So using this concept and equating the components, we can find the scalar potential phi. So using these three, we are going to prove and solve this problem. So first of all, we shall prove that the given A vector is solenoidal, for which we have to prove that nebula dot A vector is equal to 0. So now what is nebula dot A? So it will be, actually, we know that nebula dot A vector is equal to, first is dou by dou x of ith component. So what is ith component? Actually it is dou v1 by dou x. If you remember the formula which I have already done in my previous video lectures, you will understand this. So it is dou by dou x of the ith component. So that is 2x plus yz plus dou by dou y of the jth component. So what is the jth component here? 4y plus xz. So we shall write that 4y plus xz. And finally plus dou by dou z of the kth component. So what is the kth component? It is negative of 6z minus xy. So that we have to write. So negative of 6z minus xy. So that will be equal to, so nebula dot A vector is equal to, what is the partial differentiation of this with respect to x? Yz will be treated as constants and so that becomes 0. The differentiation of 2x is 2. So we have 2 over here. And here partial differentiation of this with respect to y. Xz will be treated as constant and it will become 0, and the partial differentiation of 4y is 4. So plus 4, and plus into minus we will have minus here, and the partial differentiation of this xy are constants, so they become 0, and the partial differentiation of 6z is 6. This negative sign we have already written here, so it will be just 6. So that is equal to 2 plus 4 is 6, so 6 minus 6, and so that's equal to 0. Therefore we have proved that nebula dot A vector is equal to 0. This implies that A vector is solenoidal. So we are done with the first part of the given problem. The second part is to prove that the given vector is also irrotational. Okay, so it's also irrotational. So for which we have to prove that nebula cross product with A vector is equal to 0 vector. So let us prove that now. So next we have to prove that nebula cross A vector is equal to 0, for which first we shall write nebula cross A vector, and that is equal to the determinant of I vector, j vector, k vector, and dou by dou x, dou by dou y, and dou by dou z. And here you have to write the ith component, here jth component, and here kth component of the given A vector. So if you see, the ith component is 2x plus yz. So 2x plus yz. And the jth component is what? 4y plus xz. So that we will write here. So 4y plus xz. And then the kth component is negative of 6z minus xy. So this will be negative of 6z minus xy. So we have to find the determinant value of this. So that is equal to, first we have I vector multiplied with, we have to block this column and this row, and we will have this. So this into this. So dou by dou y of minus of 6z. So I will just take this minus sign inside. So it will be 6z minus into minus plus xy. And then minus dou by dou z of this one, 4y plus xz. Next we have j vector, for which we should write the negative sign. So as per the concept of determinant, so minus j, block this column, block this row. So this into this. So dou by dou x of minus 6z minus into minus plus xy. And then this into this. So minus of dou by dou z of 2x plus yz we have. Then finally we have k vector. So plus k vector multiplied with, we have to block this column, block this row. So determinant of this matrix. So it will be dou by dou x of this. So dou by dou x of 4y plus xz minus this into this. So dou by dou y of 2x plus yz. So on simplification, this will be further equal to I vector multiplied with, what is the partial differentiation of this with respect to y? This will become 0, and here the differentiation of y is 1. So x into 1 will give us x, minus partial differentiation of this with respect to z. So 4y will become 0 because it is partial differentiation, and so it will be treated as constant. And the differentiation of xz with respect to z. So x will be constant. Differentiation of z is 1. So x into 1. So that will be x. Minus j vector multiplied with partial differentiation of this with respect to x. So minus 6z will become 0. And the partial differentiation of x, y. So x becomes 1. So it's y into 1. So y. Minus partial differentiation of this with respect to z. 2x will become 0. Differentiation of z is 1, and so it will be y. And then we have k vector multiplied with partial differentiation of this with respect to x. 4y will become 0. Differentiation of x is 1, and so we will be having only z. Minus partial differentiation of this with respect to y. So 2x will become 0. Differentiation of y is 1. So 1 into z will be z. So if you see, we have x minus x, which is 0i vector, minus 0j vector plus 0k vector, which is equal to 0 vector. Therefore, we have proved that nebula cross given a vector is equal to 0 vector, which implies that a vector is irrotational. So therefore we are done with the second proof. So first we proved that a vector is solenoidal, and now we have proved that a vector is irrotational. Next we have to find the scalar potential of the given a vector. So we know that in order to find the scalar potential, the vector a vector here, actually it is in the question, it is a vector. So a vector will be equal to nebula phi. So using this we have to find the scalar potential. So first we will equate this. So a vector is equals nebula phi. A vector is the given vector, which is this vector. So this we will take and write. So that a vector I have taken and written, and this is equal to what? This is equal to nebula phi. So what is nebula phi? Dou phi by dou x I vector plus dou phi by dou y j vector plus dou phi by dou z k vector. So this is nebula phi. So I have equated a vector to nebula phi. Now we should compare component wise. So if you compare the ith component, what you will get, dou phi by dou x is equal to 2x plus yz. So that we will take and write. So dou phi by dou x will be equal to 2x plus yz. So after comparing the ith component. So from this dou phi will be equal to 2x plus yz dou x. So taking this dou x to the right. Now we shall integrate on both the sides. So integrating on both the sides, integral of dou phi will give us phi, and that is equal to, what is the integration of this with respect to x, and this is partial. So therefore this alone we have to integrate. So 2x, if you integrate, it will be x squared by 2 plus yz will be constant. So dou x, integral dou x will be what? It will be x. So you will get xyz plus a constant c1. So 2 and 2 will get cancelled, and so you will be getting phi to be equal to x square plus xyz plus c1. You can mark this as equation 1. In my previous video lecture also, I have told you how to find the scalar potential. So in the same way we are doing here. Now secondly, what we have to do, we have to compare the jth component. So jth component, if you compare, dou phi by dou y will be equal to 4y plus xz. So that we will write. We getting dou phi by dou y to be equal to 4y plus xz. So from this we will obtain dou phi to be equal to 4y plus xz dou y. Now we have to integrate with respect to y on the right. So other variables will be treated as constants. So integrating on both the sides, integral dou phi will give us phi, and that will be equal to, the first term here is 4y. So integrating this term with respect to y, we will be getting 4y squared by 2, and then plus xz we have, both will be treated as constants, so it will come as it is, and the integral of dou y is y, so we will get xyz plus a constant of integration c2. So 2 times this is, so we will be getting phi to be equal to 2y square plus xyz plus c2. We can mark this as equation 2. Now in a similar manner, we have to compare the jth components. So what is the jth component? It is, the kth component. We have finished the jth component. Next we have to compare the kth component. That is, we have to compare dou phi by dou z, and we have to equate it to this, because these two are the kth component. So dou phi by dou z will be equal to negative of 6z minus xy. So we will write that. So from this we will be getting dou phi to be equal to negative of 6z minus xy dou z. Now we shall integrate on both the sides. So integrating on both the sides, integral dou phi will give us phi. Now that will be equal to minus, what is integral of 6z with respect to z? It will be 6z squared by 2, and then minus into minus will become plus, xy will be treated as constant, so they come as it is, integral dou z will be z plus a constant of integration c3. So 2 1 times, 2 3 times, and so the third equation of phi will be equal to negative 3z squared plus xyz plus c3. So this is equation 3. So we have got three solutions for y. Now we have to consolidate and we have to write the general solution. So if you see, we have equation 1, equation 2 and equation 3. So first what we will do, whatever is there is in equation 1, we will take and write it as it is. So phi will be equal to x square plus xyz. Constant we will add finally together at the last. So these two we will first take and write. So the general solution will be phi, which is equal to, just now we saw it is x square. So this one, that is here. First equation we have here, x square plus xyz. So that we will write. So x square plus xyz. Then we will check out with the second one. Whatever is repeated, we need not write it. So this we need not repeat. So whatever is not there in equation 1, that we will write. That is 2y square is not there. So that we will include in the solution. So 2 plus 2y square. But xyz already we have written. So this is repeated. So don't write this. Next move on to third equation that we have obtained. So if you see negative 3z square, we don't have in the solution. So include it. So negative 3z square. But xyz we have already written, so do not repeat it. Plus a constant of integration, in common we will write c. So just rewriting and arranging it in the order of the powers, we get x square plus 2y square minus 3z square plus xyz plus c is the general solution, and therefore the scalar potential phi is equal to this which we have obtained. So I hope you would have understood how to prove that a given vector is solenoidal, irrotational, and also to find the scalar potential of a given vector point function. So this is a quite important question. Follow the next video lecture in order to learn how to find divergence of the curl of a vector point function. Thank you.